Welcome back to our videocast series, Beyond the IT Headlines, where we go beyond the press releases to explain what's really happening in the world of IT and data, and most importantly, what it means for you. Today we've got a very interesting topic. Just last week, Google announced TurboQuant, a new compression technique that claims to cut AI memory usage by 6x and speed up inference dramatically. Today we're going to talk about what it actually does. What is TurboQuant? Why should it matter to you as enterprise leaders? And what should you really take away from the announcement? I'm Shawn Rosemarin, and today I'm joined by Robert Alvarez, Senior AI Solution Architect at Everpure. Robert, welcome to the show.
Thanks for having me, Shawn.
So, look, Robert, let's take a step back, right? We're kind of like, 3-4 years into this AI journey. This thing's been running at the speed of light. And one of the things we've always been talking about that seems very topical is we've seen a tremendous build-out, especially in the hyperscalers, of infrastructure to support feeding these massive GPUs and running these models. And everybody's kind of been asking the question, like, at what point do the models become more efficient? And we saw DeepSeek, and we saw what DeepSeek did on the LLM side. But this one seems more important. So let's start at the beginning. I mean, Google's always innovating. This TurboQuant thing comes out last week, and I don't know, break it down for us. What did Google announce?
Yeah, so there's a couple of things here. Like, obviously, the TurboQuant announcement is particularly focused on the KV cache, which is the biggest bottleneck on the inference side. So for these large hyperscalers, they have to maintain multiple conversations with either agents or users that are using that exact same node or that same cluster, and it grows linearly with model size and with context size. So the more context and the bigger the model, the more KV cache you need. What Google announced recently is a compression of those KV vectors so that you need 6x less memory for maintaining the same conversation. So what we're basically doing is that you can serve more users on the same infrastructure by using this TurboQuant
Okay,
algorithm.
so I want to back up a little bit because we're talking KV cache, we're talking algorithms, we're talking compression. I want to kind of come up with an analogy here. So let's assume I'm doing research, which is essentially a lot of what AI is doing. And let's assume that my parameters are the books that I'm using, all the various places I can look for answers, all the various things I know and I can search through. And we talk of parameters typically in the AI world in terms of trillions, many trillions of parameters. So call that many trillions of books. But as I'm giving answers, I'm essentially creating folders and I'm putting answers inside each of those folders on my desk, right? Because essentially that's what AI is doing. It's answering multiple questions, it's putting questions inside folders. I think what you're telling me is KV cache is essentially these folders of work, these folders of answers that I've given in the past. Is that a fair comparison?
It's a fair comparison. There's a little bit more to that as well because it also includes the question on it. So there's two sides to inference. There's what we call prefill, which is the heavy computation side, and then there's the decode, which is the heavy memory side. What the TurboQuant algorithm does is focuses on the decode side, so the generation of those folders, but those questions that you asked have a heavy compute element to it as well.
Okay, so what you're basically saying is these folders that I have on my desk is only so big, can only hold so many open folders and effectively be able to look at everything. I know you separated prefill from compute or computation, but let's just say essentially now what we're saying is, as these models scale, these inference models, and to be clear to our listener group, inference is when I'm asking the model a question as opposed to training where I'm building a pool of reference. As I ask these questions, I want to cache them. I want to put them in an area where essentially I can find the answers faster than having to go back and redo the query from scratch, which decreases latency. And once again, in layman's terms, which allows us as humans to get an answer faster in seconds versus minutes. And if it's a machine, in microseconds or nanoseconds. Is this as big as Google says it is? I mean, ultimately what you're telling me is you're going to compress what's on the desk so I can have more open folders in the same amount of space. Thereby, is that lowering the amount of infrastructure I now need, or I can actually open more folders and build more space to deliver more inference on the same infrastructure?
I'd say it's more of the latter. So when I think about it, there's Jevons Paradox from the economics that because by reducing the bottleneck in one thing, you've now just increased its usability much more. So by being able to keep to your analogy of having more folders on the desk, that means that you can have these long running agentic workflows being able to retrieve information much faster and making them more efficient, which means you'll likely use more agents in your workflows than less. So I think the infrastructure demands are going to either stay flat or even go up, but this is allowing them to be much more efficient than they are now. And one of the issues that we're seeing is just bottlenecks on inference with the large cloud providers like OpenAI and Claude, where they're having to throttle users because they just can't meet the demand.
Ah, okay. So I want to pick on one thing you said there, Jevons Paradox. Um, I don't think anybody talked about Jevons Paradox for probably 50 or 60 years. But if you think about it, the general principle of Jevons Paradox is that as the cost of a token, in this particular case, goes down, one might think then that means the overall market goes down. But actually, the cheaper it becomes to complete a token, the total cost per token goes down, more use cases actually become feasible. It costs me less to deliver the same result, and thereby things I otherwise couldn't do because they didn't make sense financially now start to make sense financially. You could look at that as the cost of a plane ticket, the cost of a liter of gasoline, the cost of a railway, sending a bunch of freight via railway. As we got more efficient, as those costs came down, those services became more pervasive. People started to use them more. So the aggregate demand went up, even though the um, incremental cost per transaction went down. That's the fundamental reasoning behind Jevons paradox. So in this case, what you're saying that TurboQuant's actually going to bring down the total cost per token for a lot of AI use cases?
Yes, because you're able to now inference and feed more users quicker. So you're able to do more with the same infrastructure. So you should be able to do it at a cheaper cost, but thus driving up the demand for more newer use cases as well. I think one of the particular insightful things here is by having more memory in the same space, sorry, I should say more of these folders on your desk, uh, these agents can do much longer thought-provoking work that just increases the what you can do with them. So there's just going to be demand driven that way.
Yeah, I mean, it makes sense, right? If I have accelerated key value cache, so I can recall conversations and answers from previous queries quicker, then I can spend the majority of my time actually going deeper on the query itself, getting more developed in terms of the responses I'm delivering. I think we've already seen this, right? In the development of, if I just look at Anthropic and I look at Claude and I look at, the Sonnet versions that constantly get released, or in OpenAI terms, right? 4.0, 4.1, 4.5. You start to think, okay, the KV cache is getting better. The learning is getting better. The parameters are getting bigger. But ultimately, I'm still paying the same amount every month to access these services. So I guess my question to you on a bit of a bigger horizon, are we just at the beginning of this efficiency cycle? Like, this is going to drive efficiency in a piece of the workflow. It's not going to solve everything. It's not a panacea. But do you think we're kind of in the first inning of this efficiency of the models? Like, how much more do we have to go here? And are we going to look back in 5 years and say, man, did we ever pay a lot to do some very simple things?
Yeah. So there's actually been a previous sort of a much lower hanging fruit development in the inference space, which was just the quantization of models, right? And that was just because we couldn't fix the KV cache problem. So we reduced the model weights so they held up less space, so that it allowed us to use more KV cache. But now we're saying, well, now here's been the real big development is now that KV cache can get compressed. But what this does is that it opens up not just high bandwidth memory or HBM to be more useful, but it opens up other tiers of memory to be more useful. You can use warm tiers that can serve caches faster to an AI fleet, and that doesn't have to reside in the HBM, but you're also sending a smaller bits of it, so you can do it faster, reduces latency. So that opens up an entire ecosystem of memory, well, I guess agentic memory workloads that can also be fed by things outside of the GPU.
Okay, so you talked about HBM there, high bandwidth memory. And look, I wouldn't be honest with my audience if we didn't take a little bit of a journey down the fact that memory is kind of a problem right now. It's kind of hard to get. I think the cost of flash, HBM, DRAM has increased by multiples over the last 6 to 9 months and has continued to, or expected to continue to grow based on unfettered demand from hyperscalers. Does this particular innovation, and we'll talk about how ready for prime time it is in a moment, but does this innovation, does TurboQuant actually help us kind of solve a little bit for this memory crunch we're in right now?
I believe it does, and mainly is because of that compression, you're able to keep more in memory in HBM or move it elsewhere at a lower latency cost and lower throughput, lower IO size. Um,
Okay, so it'll cost me less to build up my AI environment. Now, let's cut to the chase. Is this a scientific discovery that's going to require years to bring to fruition? Is this ready for prime time? What's the timeline for this to be something we're all going to be seeing and feeling in our daily lives?
I would say that I haven't seen developer movement as fast as I have with this in any other in the KV cache space. Obviously, OpenClaw is a different beast, but in the KV cache space, I haven't seen this much movement over the weekend. So I wrote a blog. We're doing internal testing. There has been a VLM developer version that uses TurboQuant. There's now a TurboQuant like pip install that you can use. So I think that in the next 2 to 3 months, we're going to start seeing the fruits of this research, and seeing what impact it truly drives. And one of the things about innovation is that when you make a big release like this, you're going to find lower hanging fruits that this now enables you to do. So we're going to see inference optimizations. One of the things that TurboQuant doesn't explicitly talk about in their paper, but that these implementations do, is you still want to have like the last 128 tokens be at full precision, because that's where the most of the context is relative to what you're generating. So like TurboQuant is like, we'll compress everything, but the developers are like, well, hold off. Give us like 128 tokens and then we'll compress everything after that. But you start hitting like the limits of what you can compress like pretty quickly and have 100,000 token windows that you're only keeping, that you're compressing 6x quite a
Yeah, it
bit.
sounds
So
like we're
it's
taking KV cache tokens and we're treating them like we have data over the last few decades in terms of hot, warm, cold. And we're looking at that by the recency rather than the usage. Maybe eventually we'll get to the usefulness of the tokens, but today it's the recency of the tokens determines how much compression, because as I compress, I have to decompress, which means I essentially take a performance hit as I rehydrate or reconstitute those tokens. So, look, let's take another journey into the future. So, this happens. I mean, you live in this space. And so TurboQuant becomes a reality, and there's other solutions that maybe from other vendors that do something similar. What's the next big bottleneck? What are you looking most forward to solving that's really going to basically crack this thing open?
uh, I think the biggest bottleneck right now is still the fact that the current architectures are, for generative LLMs, are one token at a time. There has been some work by NVIDIA and others around speculative decoding that it tries to decode multiple tokens at a time and then seeing what's the optimal one. But I think moving away from an autoregressive transformer and being able to generate multiple tokens at once should really be the next frontier. Right now, the bottleneck was KV cache. I think ultimately the bottleneck is going to be the fact that we generate one token at a time
So
currently.
simplify that for me, because that sounds really interesting. What do you mean by one token at a time? What do you mean by parallelizing these tokens? Let's try to make it as real to life as possible, because this sounds like something we should all be watching.
So if I ask ChatGPT, what is the capital of France? It processes all of that, and then it takes in that question, and the first thing it generates is the second thing it generates is capital, you know, of France is Paris, right? But it does that one step at a time. So for each single token is one compute calculation. What I would love to see is having that whole sentence be one compute calculation.
Oh,
Uh,
So rather than looking at tokens the way we do as words today, we'll have some concept of a super token that is a sentence or a group of words that can be generated in the same amount of cycle and the same amount of compute that today is a single word. Is that a fair way to summarize it?
That's a fair way to put it. Yeah.
Okay, so takeaway question. You're a CIO, you're a director of IT, you're an executive listening to this conversation saying, this sounds like it's very much in the weeds. I'm going to leave this to my AI team. What would you tell these folks? What should an executive be thinking about as they look at these developments and they take this away? And I don't know, next week in some meeting, someone says, what about TurboQuant? I mean, how should an executive be viewing this innovation and this new capability?
I would ask them, like, what are the current challenges that they're facing right now with LLMs that the KV cache or, agentic memory seems to be the bottleneck for? Because what TurboQuant's going to do is relieve that stress of the agent memory or your chat history memory and be able to do more with it. So going back to Jevons Paradox that we're talking about, like, what does this open up now if you can host more conversations or have longer running sessions with your AI that you just couldn't do before? So really think about the bigger picture.
Yeah, you know what this reminds me a lot of? I mean, in the early days of the internet, when we were paying $500 or $1,000 for an internet connection per device per month, and we thought about, it didn't really make sense for everybody to have internet access. There were shared terminals. You had to kind of find where you could because it just broke the budget. Sounds like if I'm an executive, what I can count on is whatever use cases I have, at some point in the future, the financials will make sense. If you can make the business and the concept of the engine make sense, the innovation, and this is a prime example of that, will eventually make the financials make sense. Robert, you mentioned a blog. Do you want to leave our users with a place they can go to find that blog if they want to learn more about TurboQuant?
Yes, purestorage.com. I don't know the actual full URL, but at purestorage.com/ I believe it's blogs. But it's definitely going to be on our website, and I'll be posting it on LinkedIn. I'll also share with you as well, Shawn, to share with the
Excellent.
viewers.
Well, folks, TurboQuant may be one announcement, but it's clearly pointing to a much larger shift. The AI race is no longer only about building larger models, but running them more efficiently. Efficiently in terms of infrastructure cost, efficiently in terms of overhead, efficiently in terms of power and power consumption, and efficiently in terms of empowering more use cases to be financially viable. That's where memory, caching, and infrastructure strategy matter just as much as raw compute. Robert, thanks for being here. To our listeners, make sure you like and subscribe so you don't miss an episode. For more data, tech, and IT news, check out thedatawire.com. And for Robert Alvarez, I'm Shawn Rosemarin, and we'll see you next time.